Hello everyone, this is Sarbajit Dutta and welcome back to Educathea. So in our last video, we have seen a qualitative description of blackbodies. We have seen what a blackbody is and we have seen what blackbody radiations are. We have also tried to do a graphical analysis of blackbody radiations. In this video, we are going to describe the same phenomena quantitatively. So since we are giving you a quantitative description, this video is going to be a bit mathematical, so bear with me. So Billy, will you lend me the blackboard please? Thank you, Billy. So in our last lecture, we saw a graphical variation of blackbody radiations. So we drew a graph in this particular fashion. This is my y-axis and this is my x-axis. So this is E lambda and this is lambda, where lambda is nothing but the wavelength of light emitted by the blackbody when you heat it. And E lambda is a big thing actually. E lambda is energy due to radiations emitted by the blackbody, of course, per unit time, per unit area, per unit solid angle. Yeah, so that's what E lambda is. Now, I definitely think that you know what time is, you know what area is, but some of you might not know what solid angle is. So let me tell you, you already know what an angle is, right? An angle is basically a part of a circle. So if this is a circle, then an angle is basically you take a small segment of that circle and this is defined as the angle theta, where if the radius of the circle is r and this distance, if it's s, then s by r is basically theta. Similarly, solid angle is nothing but the 3D variation of an angle. So instead of a circle, now you have a sphere, okay? Now you have a sphere. And what you do is you take a small area patch, okay? And then this will basically become your solid angle omega. We denote solid angle by omega. Omega is nothing but area of this segment divided by the radius square. So A by R square is what solid angle is. Now, solid angle looks something like this, okay? This is what solid angle looks like. Now, sometimes what happens is we get areas in this particular fashion, okay? And in those cases, you have to take the component of the area such that that particular area forms a part of a sphere, okay? So in such a case, solid angle is defined as A cos theta by r square, where this angle is basically theta, okay? Now let's come back to our original question. So we know that we got a graph like this for blackbody radiations, and since these graphs are temperature dependent, you'll get a graph like this for some temperature T1. If you increase the temperature, then you will get something like this for some temperature T2. Notice that the peak, that is the maximum value of lambda, has been shifted to the left when you increase the temperature. So for T1, let's say the maximum value of lambda is lambda m1, and for T2 it is lambda m2. So lambda m2 is to the left of lambda m1, where lambda m2 into T2 will be equal to lambda m1 into T1, and that will be equal to some constant. And this is basically what we had seen as the Wien's displacement law. Wien's displacement law. And now if you calculate the total area under these curves, then you will get the total energy, and that will be written as equal to sigma into t to the power 4, where sigma is a constant. If you calculate the area under the first curve, you will get the total energy E1 equal to sigma into T1 to the power 4, and for the second curve E2 equal to sigma into T2 to the power 4. This is basically the famous Stephen-Boltzmann's law. So Stephen-Boltzmann law. This was discovered independently by both Stephen and Boltzmann. So now the problem that I want to give you is the following. What I want to do is I want to calculate an expression for E lambda. I want to write what E lambda is equal to. If I can do it, then I will get a quantitative variation of blackbody radiation. I will get an expression which, when plotted, will give me a graph like this. Now this is not an easy job, alright? Let me show you why it's not easy. So I hope you remember how we modeled a black body, right? So what we did was we took a box, right? And we had a tiny hole here, alright? Such that when light enters through this hole, it suffers multiple reflections like this, alright? It suffers multiple reflections like this so that it never really comes out of this box, and at each point where it gets reflected, around 98% of the total light is absorbed. So there is very less probability that some light will actually come out from this tiny hole, and that's why I can call this hole to be a black body. In the same way, when you will heat this box, then the walls, which are basically coated with lamp black, they will give out black body radiations which will come out of this hole. Now you might ask that when you shine light on this hole, then nothing really comes out, right? Because it is getting reflected and thereby absorbed within this black body. But when you heat it, then light is coming out from this hole. How so? The answer is, when light is coming in, around 98% is getting absorbed at each point where it is getting reflected. So there is very less probability that it will actually come out. But when you will heat it, every single part of this inner surface of the black body will give out radiations, and that too with high intensity. So all those radiations can easily come out from this hole. There is high probability for that. Alright. So now you understand, when you shine light, then it does not come out. But when you heat it, light does come out. So now the question is, how can we model this black body using the knowledge that we already have? That is, using classical physics. Alright. So what I can do is, I'll consider that these walls have atoms like this, right? And this is a good enough assumption because walls do have atoms, right? So when you will heat this black body, then these atoms will basically vibrate because they have been given thermal energy. And when they will vibrate, since these atoms have electrons within it, when they will vibrate, these can be considered as charged oscillating bodies. And you know what happens when charged bodies oscillate? They give out electromagnetic radiations. And that's why you get light being emitted from this black body. Light is nothing but electromagnetic radiations, right? Furthermore, I will make a serious assumption, okay? I will say that the box is a closed one. So consider a closed box with length L, and the box is a cubic one, okay? Now, why I'm doing this? I'm doing this because the hole is very tiny, so tiny that you can consider this box to be absolutely closed. The next thing that I will be doing is the following, alright? I will take some random volume element within the wall of the box, alright? And what I will ask is, what is the net solid angle subtended by the hole at this volume? So I'll call this volume d tau, alright? And let's say the hole is somewhere here, okay? So the question that I'm asking is, what is the solid angle subtended by this hole on this volume? So it will look something like this. And this volume element is on the wall, okay? Is on the wall. It will look something like this. all right? This is omega, right? So the solid angle subtended by hole at a volume element is nothing but a cos theta by r square, where this distance is r and a is basically the area of the hole, that is a. Okay, so this is the solid angle subtended by the hole at the volume. Now the next question that I want to ask is, what is the fraction of radiation that is reaching this hole? All right, this volume element has atoms within it, and that's why this volume element is also emitting some electromagnetic radiations. So what is that electromagnetic radiation which is coming to this hole? All right, so the fraction of electromagnetic radiation reaching the hole, I'll call that F, and it's nothing but sigma divided by 4 pi. Now let's understand why. Now for the ones who already know what a solid angle is, you must be knowing that the total solid angle subtended by a closed surface is always 4 pi, no matter what the shape is. And for the ones who do not know, just take it for a fact. You take any random closed surface, the solid angle subtended by that surface at any point is always 4 pi. Okay, now here also we have a cubic closed surface, right? So the solid angle subtended by that entire surface at the hole is nothing but 4 pi. All right, now if you consider the total electromagnetic radiation due to each and every single portion of this box that is reaching the hole, then it will correspond to the entire 4 pi steradian solid angle. Okay, steradian is the unit of solid angle. So entire 4 pi steradian of solid angle corresponds to total energy E. So the net electromagnetic radiation that is coming out from this hole will be due to the entire box, right? And the entire box has a solid angle of 4 pi. So 4 pi solid angle corresponds to the total energy, that is E. So one unit solid angle will correspond to E by 4 pi electromagnetic radiations. That's easy. So sigma solid angle will correspond to sigma by 4 pi into E, and this is what the fraction is. This is what I have written here, right? So what I will do is I'll now write the value of sigma that I have already obtained. So I'll get a cos theta divided by 4 pi r square. All right, so till this I hope everything is clear to you. Now what I will be doing is I'll calculate the fraction of radiation that is reaching the hole due to this differential volume element d tau. So the fraction of radiation reaching the hole due to d tau, okay, and that is dE, which is nothing but the energy per unit volume multiplied by the volume element, right? So energy density U multiplied by d tau into F, because I'm calculating the fraction of radiation that is coming, right? So this will be nothing but U into a cos theta by 4 pi r square into d tau. Now in polar coordinates, you know that d tau is nothing but r square sine theta dr d theta d phi, right? So I'll put the value here, r square sine theta dr d theta d phi. For the ones who do not know this expression, particular expression, just go and check out what the volume element is in polar coordinates. All right. Just as in Cartesian coordinates, a volume element is dx into dy into dz. In polar coordinates, the volume element is something like this. Okay. Now, if you simplify this, what you will get is something like this. So u, r square and r square will get cancelled out. You'll have a divided by 4 pi, okay, into dr multiplied by sine theta cos theta into d theta, and then you will have d phi. All right. So till this point, I hope again everything is clear. Now what I want to do is I want to find out the total energy reaching the hole. Now this dE energy is corresponding to the d tau volume element. Now if you integrate it over the entire volume, then you will get the total energy due to every single portion of the box, right? So my job is to find out E, which is nothing but the integral value of dE, and which is UA by 4 pi integration dr integration sine theta cos theta d theta integration d phi. Now let's see what the limits can be. So the limits of dr will be 0 to the distance which light can travel, right? Now light has a speed of c, right? The speed of light is c, which is given by 3 into 10 to the power 8 meters per second. So the distance which light can travel will be c into t. T is time, right? Distance equal to speed into time, simple. So the limits will be from 0 to ct, right? This is the distance which light can travel, since dr is nothing but distance after all. Sine theta cos theta d theta, what will be the limit for this integral? Now you see that in polar coordinates, the limit for d theta is nothing but 0 to pi for the entire volume, and similarly the limit for d phi is 0 to 2 pi. Okay. Now I'll do the calculation. UA into 4 pi, then you have CT, right? And then you will have 2 pi from this integration of d phi 0 to 2 pi limits. You will have 2 pi here. Now for this particular integral, I will do the following. So it's 0 to pi. Now notice very carefully, I'll write sine theta into the differential of sine theta. Why I'm doing this? Because the differential of sine theta is nothing but cos theta d theta, and that's what I have over here. So I can break down the integration in this particular format. Now the job is simple. This integration is basically of the form integration any limits x into dx, which is nothing but x square by 2, right? So I'll carry out the integration now completely. So UA divided by 4 pi into, you have 2 pi over here, into CT, and this will be basically sine square theta divided by 2. So sine square theta divided by 2, limits from 0 to pi. Now sine 0 is 0 and sine pi is 1. So if you put the value of the limits, you'll be getting nothing but a half, right? So now let's carry out simplification a bit. Okay, so you have 2 pi over here, you have CT, and then you have half. So 4 pi and 2 pi will give you a 2 in the denominator, and then you have another 2. So UA divided by 4 into C into T, right? So this is what the total energy is. Now energy per unit time per unit area and per unit solid angle is also included because I used the fraction of solid angle in my calculation, will be nothing but E divided by area divided by time, right? And this is nothing but UC by 4. I'll call this E lambda because I'm doing my calculation for a particular wavelength. In my entire calculation, I have been calculating how much electromagnetic radiation corresponding to one particular wavelength has been reaching the hole. Never in my calculation I have considered all the wavelengths. If I did so, then I had to integrate over all wavelengths. I haven't done so, right? So my calculation is for only one particular wavelength. So this is what I get. I'll write it over here once more. E lambda is equal to C by 4 into U, where U is nothing but the energy density, right? U is energy density.
Thank you so much for watching this video. Do not forget to like, comment and share this video with your friends as much as possible. And also don't forget to subscribe to the channel because that would serve as a motivation for me to come up with more such beautiful videos. Also kindly press the bell icon over there so that you get a notification each time I upload a new video. Don't forget to check the description box down there for more updates and have fun and enjoy science.